Okay, I think that's working. All right, everyone that's here, you should be able to see. You should be able to see the screen. You should be able to see the chat. Please use the chat. It makes a huge difference. Sorry about the delay, but YouTube was being stupid, and I was able. Just like to clear everything, and I got it working again. So some people are asking about the hurdle already, and that's not what I want. And my computer's going slow, which is great. Just can you please let me know in the chat if you can hear me? Okay, so hopefully you can hear me. I'm talking to myself. Either way, it's all fun. So the hurdles, and I may have said something different in the labs. You have to get 50% for the exam and 50% for the subject. Okay. So theoretically, you could end up with a 74% and still fail the subject. But that's very rare. So you have to get both of these to pass the subject. All right. You can't hear. Can everyone else hear? I might grab the other keyboard as well. Be a good idea. All right. So what I'm going to do to start off with, just so that we can kick things off, I'm going to start with something harder, and then we'll go to stuff that's easier. So I'm planning to just start off with the uncover the zeros function, just because there's a lot of questions around that. And then we'll go on to some easier concepts. I want to go on to lab 12 as well, and any questions, and then previous year's exams, and anything else. And tomorrow we're going to do another session, and I'm going to do similar things, but I'm also going to try and link your knowledge into what it means in terms of computer. And so I might introduce you to assembly. I won't teach you anything, but just so you understand the concepts deeper. That's what I was planning on doing. So I want to start with this uncover zero function, because it's actually a really good question to see if you understand logic. And logic is really important when you solve questions like the flow diagram, or the what was the other one? The last question where it's just text. So I'm just going to make a quick board. So if this is a bit beyond you, don't stress. I just want to go through it because there's lots of questions about it. But yeah, it's good. It's good knowledge. So I've got this board here, and what I'm going to do is make it a little bigger. So we all had boards in our game. Now, you would have seen in the help sessions or live streams when we were doing it, we talked about having 4 variables per location. Okay. And 3 of these variables were in a status register. You'll see why I called that as well, just to introduce you to a concept tomorrow. What's the average mark for assignment 3? I don't know, actually. I might check that when I have a break. I didn't actually do that stat. I have been trying to get all the marks in, which is not an easy task. All right, so our board looks something like this, and we had 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. So this is a 4x4. As we remember, the outside is the border region. Now, with this, let's say this is if it's revealed, this is if it's a flag, this is if it's a mine, and let's say this is its value. Okay, this is just a notation that I'm using just while I'm sketching it out. Now, what I want to do is make up a board. Now, these outer regions, we set all these to revealed originally. And we set the values to 0. Okay. Now, anyone joining, just as I said, we'll go on to easier stuff. I just wanted to cover this because I did have quite a few people that did do the uncover 0 either poorly or very poorly. But some of them worked. We then have some mines which are randomly allocated. So I'm going to put a mine here. Okay. So I've got one mine there. And I'm also going to put a flag. I don't know why I put an M there, but that doesn't really make a difference. I might actually use a different color. So there's one mine in total. And I'm going to say there's one flag as well. Okay. And then we just need to set the values. So we have 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Oops, I made a mistake. 1, 1, 1, 1, 0, 0, 0. So we have a whole heap of zeros. Okay. Now this is quite important. So we're now going to have a look at a couple of solutions. And we'll start off with the simplest solution to these uncovered zeros, just to understand how to go about this. Now, I'm not going to go too much into depth into the recursion side of things because we've already done that. But what we're looking at is any of these zeros here. I'll just add a layer. So if any of these zeros here are hit, and they're all touching each other, then we should reveal, give me another color, all of this. Okay, we don't want to touch the flags and we don't want to touch the mines. All right. As I said, if you're joining, don't stress. We will go on to a lot easier stuff. I can see people are slowly joining, so that's why I wanted to start off with something harder as well, so no one misses anything basic. All right. So depending on which one we pick, we need to branch out and attack all the surrounding zeros. So if I choose this one, if I choose this one, if I choose this one, no matter what, I need to look around all 8 that surround it. Okay. So that sounds like a for loop inside a for loop to me. We have the X location, we have the Y location, we have the mine board, we have all this information that's here. And all we really need to know is if it's not revealed and it's not a flag, and the reason we don't care if it's a mine is because the zeros can never have a mine surrounding them. So this bit here, for any of the ones that surround, should never be set, or else we've done something wrong. Okay, so I don't have to worry about this bit. Okay, so that's the first little bit of optimization I can do. I do not need to care about the mine. Does that make sense to the people that did this? Yeah. Does that make sense so far? Or are we delayed? Or are we? I don't stress too much, but those that did this, does that make sense why we disregard the mine bit? I'm not getting anything from the chat. It's a little odd. All right, so I'm going to say that we clicked on, say, this one. Okay. I'm going to say we clicked on this one. Now, when I go into each one of these, all I need to check is it not a flag and is it not revealed? And if it is, then we set it to revealed. The reason we set it to revealed is so that when we go into this next one, we don't repeat the operation over and over and over again so that they keep calling each other. And we also need to check if it's 0, one of the surrounding ones, and if it is, then we call the function on that and we end up with recursion. Okay, so a reasonable answer would have been something that looked like this. It's not the greatest answer, but it's a reasonable answer. So we've done everything that we've said there. We've got 2 for loops. Okay, 1 and 2. We have our I and j, but we don't want to start from 0, 1, and -1. We want to go y plus -1 and x plus -1 and move up so that we get the surrounding pieces. So we have -1, 0, 1, -1, 0, 1, but it's x minus 0, 1, x plus 0, x plus 1, y minus 1, y plus 0, y plus 1. Now, that's all good. So we just check, is it not revealed and is it not a flag? And if it isn't, then we make it revealed. And if the value is 0, then we just recursively call the function. Now, this is quite a lot of checks still. Now, one thing that you should notice is a pattern. All the ones we want to check are in this block here. Okay, we don't want to check the flags one. And we'll notice that all three of these are all 0. Okay, so we can use that to our advantage to make some optimizations. Okay, so I'm going to give, so are we happy with that version? So as I said, anyone here, I will be going on to easier stuff, but I just wanted to cover this because I think it's quite good for those that are quite ahead. All right. So finding patterns is really important because it means that we can optimize that code. So the next version, which is a lot better, but not perfect, is this. So I've dropped the number of lines and I've dropped the number of operations. The number of lines isn't too important. I don't really care about how many lines there are. I more care about the number of operations and what those operations are and what we're doing. So here, I've only got one if statement. Okay. So let's have a look what I've done. So I'm still going around and I'm using a ternary operator. Now, this is important that you understand what the ternary operator is. So condition, value if true, value if false. Okay. So if the status byte is 0, okay, then that would be false. Okay. Sorry. Damn it. Okay. What's that noise? Okay. So if the status byte is 0, then it would be false. So it goes over to here. We can see these little columns here. If it's true, meaning that one of these are set, then we just return 0, meaning if 0, and just skip this and continue through the loop. So if it's false though, meaning they're all zeros, which is what we want, then we get over here and we've got this big operation. So we've got mindboard ing dot status byte or equaled to 4. Now that is very similar to this. Not this, sorry. Very similar to this. It's pretty much the same thing, except for you get rid of the shift because I know that revealed is in bit 3. And we know 100 is equivalent to 4 in decimal. Okay, so I set that in the status byte to revealed. I then shift by 3. So I just make this 0 for my equation and add the value. If the value is 0, then I go on to the uncover zeros. Okay. So this combination here may take a bit of thinking, and I've got the not there, so it's not. Because if it's 0, then that would be false, but we want 0 to be true, so I add the not. So this is looking a little bit more complex, but we've still got a couple of problems. Okay. So the first problem is that I'm always checking this middle one, which I don't need to check. I'm already in that one. Okay, we can see our for loop goes through that. The other thing is, if I'm here and I call this one here, then the problem is that we still check. We still check this one, even though this one's going to do that job. Okay? We may actually be able to make another optimization. But we'll leave that for now. No, that won't work. All right. Okay. So I'm going to go on to the next one. There's only two more. And then we'll get to the revision while everyone's getting in on the conversation. All right. So next version is a lot more optimized. And this is where logic becomes really important. And also understanding that the reduction of lines doesn't mean faster code. So here, I've got a lookup table. Now, this may seem strange that I'm introducing a new variable, but it means that I can ignore this center one. Okay. It also means that I can do something a little different. So before we were traversing, going like this, where what I want to do is traverse like this. And there is a reason for that. Okay. And I think I hinted at that in the help session, an earlier one. So we have a bunch of values here, and all they're doing is just telling me all the positions in that order. I'm then just looking them up. So I just grab the first one for each x and y, and then just add them each time and do the exact same operation here. I also have this plus plus I here. Now this also speeds up our operation, because if I call this one, I can ignore this one. I actually can ignore this one too. But if I add too many, I don't get the corner pieces. So I can only skip one. I may be able to further optimize it and skip two, but that's what that plus plus I is. So we have even less checks. So we've got rid of this here, and for every 0, we've got rid of the condition. So this speeds it up. Now, this recursion can end up quite large, and this is why this whole optimization is important. Now I'm going to go one further. Now I'm doing all this with what you know as well, so I'm not introducing any other concepts. This is all stuff that you've covered. Now the next one's slightly strange because I actually add a line. So I'm just going to put all these here so you can refer to them. So this one Instead of a two-dimensional array, I make a two one-dimensional arrays. Two one-dimensional arrays are going to be faster. I copied the wrong thing. Sorry. That should be. Oh, there's a mistake in the other one as well. Ignore my mistake. It should be X. Okay. That should be that. And neither should that. All right. So we're getting pretty close. And I'll give you the final version. I won't explain it too much, but you can see how we can get to a more optimized state, given what you know as well. And that's the important thing, is that this isn't beyond the scope of what you're studying. But programming and logic at the low levels for very, very fast code is very, very important. And so I just want to give this example just so that you understand that, that what you have can be quite powerful, but by itself, without you using your logic, it's only as powerful as you're trying to apply it. We can always solve a problem with C or any language really, but how well is the other question. So this is the final one, and this uses bitwise operations instead, because bitwise is slightly faster. But yeah, and there's a little bit of math involved in that. There might be better ways to go about this. This is a unique case. This isn't actually the Minesweeper rules for this uncovers. So to do that is actually a little bit easier. But yeah, so I just wanted to do that quickly and get that out of the way. And I think it's a good introduction to anyone that wants to go on further with programming, just to understand that the language is not enough. The logic is important too, and that's why there's the coding questions and the what's it called, flow diagram questions, etc. Right. So if you're still here, just say hi in the chat. Oh my gosh, Facebook. And we'll go on to the next thing. And this will be more interactive, so please use the chat. Now, another thing is that, yeah, no one really had a very optimized answer for that. But there were some that were close to the first one I showed you, or pretty much the same. That's the naive approach. Where the hell am I? All right. Oh, my computer's going slow. All right. So what I'm going to do is give you a couple of questions. I'll give you a couple of minutes to solve them. Now, I did get asked to go over this. Leave that for a couple of seconds. So I'm going to put 3 questions up. If you're here, please try answer them like you're on an exam. If everyone gets them correct, then I don't know. If you don't know the answer or you find it very difficult, say so. I don't want to cover absolutely the whole subject again. I don't have 12 weeks, so if everyone gets the answer and you stay quiet, then I'll assume that everyone knows it. So please use the chat because it's really, really hard to judge what people know and don't know. And I will assume otherwise. So I'm going to put 3 questions up. I'll give you a couple of minutes. Try those, and then we'll keep going. So everyone in the chat, put your answers, and if you don't know, write "don't know" or something similar. Okay, what's your answers? So if you're watching, please put your answers in the chat. Or don't knows, if you don't know. You're going to be doing this in the exam, so it's good practice. Okay, we'll put what you do know and put what you don't know. All right, so we've got a couple of answers there. I think most people understand some of them, but we've got a couple of problems. So anything IO related, Okay. Anything IO related is going to be standard input and output.h. So A and D are both standard IO.h. Okay. We have to remember that standard in and standard out for us in this subject, standard in is just the keyboard and standard out is the screen. Okay. So if we use fprintf and we go, we remember the first thing is our file pointer, then we can go standard out, hello world. Okay. So these are called streams. There's also an error, standard error as well, which was mentioned in the lectures, which will print out error messages for you. Okay. Now, we notice that fprintf does exactly the same thing as printf, except we just need to specify the file pointer. Okay. And these streams, your keyboard and screen, are also file pointers, which was in one of the lectures. All right. And so that's why both of these are standard IO.h, and we've also got another one. I didn't read them all. Opening a file is also standard IO.h. Comparing two strings, we have a whole library of string functions, which is string.h. The last one is a bit of a trick question. Obviously on an exam we won't have trick questions, but this lab was purposely set up to be tricky because I like trick questions because it makes you remember. We have the function size of. Okay. This doesn't have a library, it's part of C. Okay. So it's not in any of the libraries. All right. Okay. So just be aware of that. All right. Second, 4. Go. Put your answers for 4. Most people got it. Some people are using type defs. I'm not going to use a type def because I don't want to confuse everyone. Okay, if you want to use type defs in the exam, that's perfectly fine. But we've just tried to avoid using them this year because we want you to understand that relationship. All right. So we want to struct. So we create a new type with the tag name. This is called the tag name. And has member variables. So members go in here. And we have name and age. Okay. Name is a string. So a string is an array of characters. Now, I should have like a bit of an indentation there. Of 80 characters, and age is an int. Now, make sure semicolon, semicolon, semicolon. Okay. I think most people have got that quite correct. Okay, so everyone seems to be fine with that question. It's a fairly easy one. All right, number 5. Now this one's a really, really important one. And we're talking about in C, okay, not in other languages, because it does change. But in C, it is actually defined as a specific size, unlike int. Okay, the pain question. So we're doing 5 minus my computer. Stupid. Yes, you lose. So so a couple of questions we've had. So in the exam, without time constraint, we lose marks if we forget a semicolon. Yes, you may, but it'll be half marks. Okay, so any question with writing, it is, most of them are broken up into about 4 or 5 points or something like that, and there might be 1 point for semicolons or something like that. All right, the second question, should that be 80 plus 1? It depends on if you're actually wanting it to be 80 ASCII characters plus the null terminator, or if you want it to be 79 plus the null terminator. It isn't really defined here, so considering it says 80 characters, the null terminator is a character, so that's 80 characters, and you would assume that they're only going to use 79 of them. Now, what size in bytes is the storage type car? 1. Okay, this is something you need to know. So 1 byte is 8 bits. 1 car is 1 byte. Okay, this is very, very important. Now, if you've done Java, you'll know it's a different size in Java, but in C, it is always 1 byte. No matter what system you're using, it is always 1 byte. Okay. This is a very, very important concept that you need to know. Right. So let's skip past a couple of questions now. So this one is another one that I like. So if there's any questions. So in int, it depends on what system you're running. So an int, so C is a system-dependent language, as we learned when we did all the pointers stuff. Now, an int will change size depending on what system you're using. So on a 16-bit system, it'll be 2 bytes. On a 32-bit system, it'll be 4 bytes. On a 64-bit system, it'll be 8 bytes. And so, as you know, when you use Windows 64-bit mode, it actually all changes. So in int, is system dependent and will change depending on the system. And that's why we don't really care. However, we're using a 32-bit system, so on the Unix machines, which is consistent with x86. All right. Would help if I put the question up. Okay, so I'm going to kind of add to this question as well. So a little bit more to it. So what is a character literal? And give an example. This is a really easy question, but it's something that you forget. Most people forget fairly quickly. It's right at the start of the subject, but you've been using it the whole time. So go ahead, chuck your answers down. We'll go through it. If you don't know, say don't know or something similar. Or you're saying this is boring or don't care, or etc. Just say. While I do that, I'm going to make another question. Okay, so once you see this, it's quite important. So a literal is a concept that's very, very important. We have variables and then we have literals. So a literal is literally that value. So let's start with a simpler one. So let's go a decimal literal. Is going to be, and we'll say an integer decimal, is going to be 85, for example. Okay, that's an integer decimal literal. Okay, it's literally the number 85. A character literal is literally the character A, and it is specified with a single quote. All right. So any character like this is a character literal. All right. This is an integer decimal literal. We could have a floating point literal, which will look something like 6.3. So, for example, I can have int a becomes the character A. This is a variable. This is a literal. Okay, it's literally that character. All right. We also have some other interesting literals which you've seen. So, for example, some of the ones that you've seen. So you've seen, let's say, 85 with an L at the end is a long decimal literal. We also saw in some of the labs the big L at the end of floating point, which made it a double. Okay. We also saw integer, let's say, hex literals. So 0xFF. We saw integer binary literals. Now when I say, I should actually say integer, not int. I'm just being naughty. Integer binary literal. So something like that. Okay. Okay, so these are all literals. Now, the biggest mistake that a lot of people make is the difference between this and this. So this is a string literal. This is a character literal. Okay. So the big difference here is this one here is an array. Okay. This one here is not. This is an array of characters, finishing with the null terminator, which is 0, where the character literal is just a single character. Okay. So a string literal can have multiple characters. Okay, and here we've got 4 because we have that null terminating character at the end. Now I'm going to ask another question related to that, because I think it's quite important. So give two examples of integer types. I should say integer. I should say classes. That'll make more sense. All right, so this is my next question. So these are just common pitfalls that a lot of people make. So I think most people here have got the right idea. So things like car, unsigned car, int, short, etc., long, unsigned, signed, whatever. So these are all integer types, meaning they can have whole numbers. And I just want to point that out because a lot of people get confused with this and this. It's a bad, I wouldn't say a bad naming convention, but it's a confusing naming convention. Okay. Yeah, unsigned int. There's another one. But all of these are integer storage types. They all hold integers, including car. Okay. I have a very difficult question relating to this, which I was reading. I might actually show you a little later, because I think it's quite important. But I might leave that for a little bit later if I remember. Just the pitfalls of the car. All right. So we're happy with literals. Is there any questions about literals? So that's just a real terminology question. Remember, we're testing your theory. So make sure you know your theory and your terminology. This is why I give you this also, this integer storage class. Okay. So I'm going to write another question. So, hash includes, I don't know why I'm writing that. I don't really need to. Main int A is, let's say 2, int B is 4, int C 6, int D is 2. Then we go float E becomes float A divided by B plus D divided by C. And then I'm going to go printf. D, oh no, sorry. I'm kind of writing on a bit of an angle here, which is kind of the line as well. I think everyone's pretty confident. What am I doing? Not 2F, sorry. E. Sure. All right. So write down your answers to this question. And give you justification as well. There's no right answers here. Oh, there's answers now. Yes, we'll get to bitwise. Don't worry, there'll be heaps of bitwise in these. Does everyone put their answer? Anyone else? Okay. So this is a really good question for understanding the typecast. And there's only 2 people that have got it right so far. The answer is 0. Okay, and this is one of the first things we did in the subject. Okay, and one of the first things that was covered in the second week lab. That was a big part of the lecture. So we need to have a look at this equation here. So we have float a over b plus d over c. Now, most people picked up that there was one person, that the d over c would result in a 0. So let's have a look at this and plug some values and then their types next to it. So we've got float, we've got int plus int over int. There's no brackets there. And we've got float, we have those 2 over 4. That's my pen not working. What's going on? Plus 2 over 6. Okay. So we have a look at the bracketing and we see that we have these inner brackets here. So this needs to be calculated first. Okay. Before we can apply this cast. So we have an int and an int, which is the largest type, an int, and hence 2 divided by 4 results in 0. So we have a float, we have an int plus an int over an int. We then have the typecast, so we end up with 0.0. So we have a float plus an int divided by an int. And we have 2 divided by 6. The division takes precedence over the plus. An int divided by an int, the largest type is an int. So we get 0. We have a float plus an int. The largest type is a float. And we have a float plus a float, so we get 0 plus 0. I'll put the 0.0 to make that obvious. And so we get 0.0. And that gets stored into a float, so that also gets converted to a float before. Now the question. Firstly, if we wanted to fix this, how would we fix this? If we actually wanted these divisions to work, all we need to do is get rid of these brackets here. We'd also need to add a typecast to one of these. Now, there's multiple ways we could go about this, because we can typecast A or B, D or C. Okay, it's up to you which ones you want to cast, and that would fix it. But because those were in brackets, this happened first. If these are in brackets, that's fine. It does the typecast first, and then this happens. Same with this if this is in brackets. So you have to be careful with your brackets. Now, someone asked the question, what happens to 1.7? So we have an integer type, and we just asked this question before. Okay, so int is an integer type. And we want to put this 0.7 in there. But it can't. It can't store this part inside this type. So all it's going to store is the 0. It doesn't care what's after it. It can't round it because it can't even store it to round it, because there's nowhere to put this 0.7. So an integer will always truncate because there is nowhere to store this 0.7. Okay?
Now, there are ways of doing fixed point math, but it is very, very difficult. But very, very fast. Okay? So that's the reason that it doesn't round, is because we don't store it anywhere. Compared to, let's say, percent %.2f, which is a format specifier, it's got somewhere to store it. Okay? And it's a conversion to a decimal number. Here, it's just storing the number. Does that make sense? I thought that was a good question. All right. So, we are going to go over bitwise, but I want to do that all together because there's so many questions on it, and it is a big part of the exams generally. All right. Okay. Now, someone sent an email about this question, so I'm going to put this out. It is quite a good question. So I'm going to take a quick break. So chuck my dinner on. And I want you to, I wonder if I can make it bigger actually. Let's not do that. Let's go like that. Let's go like that. Let's go like that. Like that. All right. This is an excellent question. I'm going to have a quick 5-minute break. I'm just going to put some food on the oven. But have a go at that while I'm gone. Or take a break yourself if you've already solved it.
Unmuted. Cool. All right. We all still here? Say hi if you're still here. We'll go through this question. Hopefully I don't make a mistake. All right. Cool. All right. So we are going to draw out our variables. I'm just going to draw this out fairly rough because I did an exam. So I've got num. Now it's an array of 4. We don't need to specify the whole array. We can just put a 0 and they'll all be zeros. Okay. So that's a 0, that's a 0, that's a 0, that's a 0. Okay. We also have count, which is also a 0. Okay. Well, count is less than 10. Yeah, count is less than 10, so don't worry about that. I think most people have got this, so I'll go through it fairly quickly, unless there's anyone that hasn't got this. So we get a character, and we've got an input buffer here. So we grab the A, take that off the buffer, and we store it in CH. So we've got the character A. Okay. If CH is greater or equal to the character literal, and CH is less than or equal to this character literal, then we do this. So we know that this has a value. Okay, so this is 65 in decimal. We can convert that to binary and hex as well if we like. We'll go through conversions a little later. But if A is greater or equal to A, meaning if you want to think about it in terms of decimal because you're more used to it, is 65 greater or equal to 65, or is A greater or equal to A? Yes. Yes, it is. And is it less than or equal to D? So we know on our ASCII table that the numbers, the capital letters, go up sequentially. So 66 is going to be B, 67 is going to be C, and 68 is going to be D. So is it less than that? Yep, all good. Then we've got CH minus A. So A minus A is going to be 0. So num plus plus. So we get a 1 here. Okay. So num 0 plus plus. And I'm not creating another layer, so I can just show you what's there. So we can ignore the else, and count goes up by 1. Okay. So we get a 1 here. We then go back up, because we're in a while loop. Is count less than 10? Is 1 less than 10? Yep. We get the next character off the buffer, which is another A. Cool, we've got another A. If CH is greater or equal to A, we already know this is true from the last time we went through, so I'm not going to bother checking. And we know this is just incrementing this first one. So we have a 2 here. And count goes up by 1. So we have a 2 there. We go back up. Is 2 less than 10? Yes. We get the next character, which is a capital B. Okay. So we've got a capital B. Is that between these numbers? Yep. B minus A. Now, knowing the ASCII table is in order, 66 minus 65 is 1. So this is going to be a 1, meaning that we have a 1 here. We then go count plus plus, and we get a 3. We go back up. Is 3 less than 10? Yes, it is. We get the C. Same thing. So we've got a C in there now. C minus A is going to be 2. So we get a 1 here. Okay, count goes up, so we get 4. And this is the one that most people get stuck on. I'm going to go ASCII table just to show you. You really don't need the ASCII table in this or this question or the exam. Hopefully that copies across okay. So this is our ASCII table. You can see here that A is 65, B is 66, C is 67, D is 68, or in hex 40, 41, 41, 42, 43, 44, which is nice. We can also see that the lowercase is 97, 98, 99, 100. Okay, so they're not in that range. Okay, so I'll pull that up again just so you can look at it in decimal. So that's 97. So little, and it doesn't matter if you don't have the ASCII table because you don't really need to know that little case a is 97 for this question. You just need to know that it's not in between this range. Okay. All right. So now I've lost where I am. So we get here, and what are we up to? We're up to this A. And so this isn't true. Okay, we've got a lowercase a here. And so we get to this break. So we break out of the loop, and now we print. So we get 2, 1, 1, 0. Okay. So the break takes you out of the loop that you're in. Which I might actually show you another example of a loop with a break, just to reinforce that. Does that make sense? So, no, I'm go away. So, the other people may have been right if there wasn't this break here, but because of this break, we have this problem. Okay. Now, just as an example, if I have 2 while x, I'm just making up some example 4, there's a while, and we have a break, let's say here, this will break from the for loop. If we have a break here, this will break from the while loop. If we have a break here, then we'll break from the do while loop. Okay, so it'll take you out of the loop that it's in, not the outer loops that it's in. So if there's multi-layers to the loops, then this break will only take you out of this while. This break will only take you out of this for, and this break will only take you out of this do while. Okay. It's interesting what some people do for exit conditions because of that. All right. So I've got this question. And this is a really, really good question. Because it has something that you didn't see much of in the labs and stuff, and it's quite important that you understand when and when not to do this. But have a quick go at that. I'm going to go through it. Okay. So the main thing here is the fact that you've got a global variable, which is this external, meaning its scope is pretty much everywhere in this file. So just be careful about global variables, because if you have multiple objects or multiple files, that may not be true. Why did I just get rid of Y? All right, so let's have a quick run through this, and then I'm going to have a 20-minute break for dinner, and then we'll be back. All right, so we've got this global variable called external. It's going to write axt. We've got some variables in here, which is x, y, z. But I'm going to go through this step by step. So when creating your variables, try and create them step by step. So we have func5, which passes 5 into x. Okay. This is local to this function. So we have external, which is 0, and we have 0 plus 5 gets stored in temp. So we have 5 here. External takes on x's value. So we have 5 in here. And we return temp. So x now has 5 in it. Okay. We then get, so we leave this function and we lose all reference to these variables. And we get here. So we create y. And now we call y and we pass the 1. So x has a 1 in it. Now, as I said, if I'm going too fast or too slow, just let me know. We create temp. We have external, which is 5 plus 1, so we get 6. External takes on the value of x, so we have a 6 here. And then we return temp, so 6 comes back and gets stored into y. We then have z or z, and we pass a 2. So we have a 2 there.
We create temp again, and we have 6 plus. Did I update X? I don't think I did. It should be 1. And then no, then we get 3 because we have 2 plus 1. External becomes 2. The 3 is returned, and so we print 5, 6, 3. Okay. Right. Are we happy with that question? He's still here. There's lots of people watching. There's not many people interacting. So if you don't know, say don't know. If you do know, say the answer. Because I don't know what you don't know. I'm just going to rush through it otherwise. This is lab 12 from last year. All right, so what I'm going to do now is I'm going to go eat. So I will leave you with some questions where you can go do the same. Oops, that's not a good size. And when I get back, I will go over a lot of binary stuff because I think that's where a lot of people struggle. Well, that's a good question. Yeah, I made a mistake. Well, it's kind of a bit hasty. Where it says external becomes X. I just did it after. That's also a good question. This is a good question. Okay. So I'm going to go. Alright, so I'm just going to go quickly eat something.
this is the pain of starting this early. Well, it means we can keep going till late. But yeah, I'll be back in about 15, 20 minutes or so. If you want to try these questions, feel free. Need some standby music or something.
Okay, I'm back. Who's still here? Say hi if you're here. A couple minutes. Go through these questions. Okay, let's start with 25. So what value does argc have in this case? If you don't know, say you don't know. Okay, beautiful. So everyone put 4, and they're wrong. It's 5. Okay. The program name is also counted as an argument. We need to remember this, and it was in the practice. So argc is the argument count. Okay. This is argument 0, 1, 2, 3, and 4. Okay. 1, 2, 3, 4, 5. All right. So the answer is 5. So these are little mistakes, but these can be a full question that's, let's say, multiple choice that you get 0 on. So you need to be careful with this. All right. We also have argv, which is the argument vector, which holds the strings. So argv 0 would hold the string calculator, and so on. Okay. Are we happy with that? So yes, you're happy. No, you're sad. You would like something further explained. As I said, please interact. This is really important. Cool. All right. Wait till there's a couple more yeses. All right. So now I'm going to go through this one, or I might just go through it. So we have int r5 1 5 3 2 4. Now we have to remember with an array that we can refer to our array as a pointer, or as the whole array. Okay. So we have 1 5 3 2 4. Now these are ints, which will assume the 4 bytes. Doesn't really make much of a difference. We have x, which is 0, and we have this pointer. So we have p. I'll do it properly. We have P, which is an int star. Now, ARR is a pointer to this first memory address. Okay, so ARR holds a memory address, and that memory address gets stored into this pointer P. Okay, now this star here is not dereferencing because it's used during the declaration. Okay, so remember in week 7 or 6 or whatever, we had 3 different uses. This was multiply, this was declare a pointer, and this was dereference. Okay. So we can say P holds the memory address, so address of R, which is actually this address here. Even though there's a 4 byte, it always points to the first byte. So don't forget, each one of these is actually made up of 4 bytes. We'll get to the binary stuff soon. And so we have a pointer to this first element. We then have while P is less than ARR plus 5. Now, ARR is a pointer to this first memory address, and we have this plus 5. Now we have to remember that it is ARR plus 5 times size of int. Okay, we saw this in lab 5 or 6 or 7 when we did the lab about pointers. Okay, so this plus 5 won't go 1, 2, 3, 4, 5 and end up here. Okay, it will actually go 1, 2, 3, 4, 5. So it's actually pointing at the memory address after the array. Now, that's not too big of a problem, as long as we don't read from here. Okay, so this here could be illegal. All right, this could be illegal memory, but as long as we don't read it, it's fine. We're allowed to point at it, as long as we don't read it. So is this pointer here less than this? Now we know that the memory is sequential. So let's say this is 0x 0, 4. This would be 8. This would be 12. This would be 16. This would be 20. This would be 24. Okay. Yeah, that'd be in decimal. So 24, 4 is less than 24. Okay. Or we can just look at this diagram and know, yeah, this is definitely less than this. Okay. Okay, because it comes before it in memory. So this is true. Now we have the dereference, which is this star. So dereference P, meaning we have P and we go to where it points and we grab its value, is 1 greater than X. Yes, 1 is greater than X. Then X becomes dereference P. So dereference P, we go to P, we go where it's pointing to, we grab its value. So 1 gets stored in X. Okay. We then have this addition of P, so this increment. Now, we have to remember, once again, that this is P plus 1 times size of int, because it's not going up by each address, it's actually going up by ints, and that's why pointers are so powerful and why we spend so much time on them. So we go up by 1 int, and we end up here. We go through the loop. Is p less than ARR plus 5? Yes. We then dereference p, so we get 5. Is 5 greater than x? Yes, it is. 5 is greater than 1. So x becomes dereference p, so x becomes 5. We then increment p, so once again, we add 1 int, and we go back up. Is p less than ARR plus 5? Yes, it is. We dereference p, and we get 3. Is 3 greater than 5? No. So we skip that, and we increment p. So we get here. Is p less than ARR plus 5? Yes, it is. So we keep going. Dereference p, 2. Is 2 greater than x? No. So that gets skipped, and we increment p again. So now we're pointing here. Now, is p less than ARR plus 5? Yes, it is. Dereference p, is 4 greater than x? No, 4 is not greater than 5. So we increment p again. And now we're pointing outside of our array. And as long as we don't read it, it's fine. Is p less than ARR plus 5? No, because it's equal with it now. And so we print out 5. Does that make sense? Say yes if it makes sense. Cool. All right. So let's go to this last question. Okay. So if you have any questions as I go, don't be afraid to say. If you don't understand something, don't be afraid to say. It's your exam. Ah, damn. All right. So now we've got 23. We have I, we have a pointer, and we have this calloc here. Now, calloc and malloc are very similar, but they share a slight difference. So we'll copy to the arm. Malloc has 1 argument. Okay. Calloc has 2 arguments. In malloc, generally we go n times size of something, where in calloc, n being the number of things and size of their size. Now we can do more elaborate things, but for this subject, we can just keep it fairly simple, and that's all you're really going to keep it. The difference here is we have n and then the size of those things with calloc. And this is one of the reasons I don't like calloc. The other thing calloc does is it initializes the memory to 0. So all of the places are 0. All right. So that's the major differences between them. So this is memory allocation, this is clear allocation. So here we create 5 ints. 5. And this returns a pointer to the start of the array. Go down here, point to that. And we know that they're all zeros because we use calloc. We then have a for loop, so we set I to 0. Is 0 less than 5? Yes, it is. We dereference our pointer, but because it's on the left-hand side, we're storing something into it. I'm on the wrong layout. So here we're going to store I, which is currently 0. So 0 is here. We then increment our pointer. Now, I've lost what layer this is on. It's great. Ooh, that's a really good question. I'll answer your question in a second once we get to the end. Now, we're then incrementing our pointer. As we saw before, it will go up 1 int because it's an int pointer. Now, this, I do not recommend you do. If anyone can tell me why in the chat, I'd be glad because it means you've listened. We then go back up, we increment I to 1. So someone tell me why this is bad, what we're doing here. Is 1 less than 5? Yes, it is. We store 1, where pointer points at, and then we increment pointer. Once again, something bad. If someone can tell me why it's bad, I would appreciate it. We then go back up, I gets incremented, so it's 2. Is 2 less than 5? Yes, it is. So we get 2 here, and we increment pointer. And we get to here, and increment is 3. And so we can see that at the end, we are currently pointing at nothing, but that's okay at this stage. And now we are going to reset I to 0. 0 is less than 5, and pointer decrements by 1. So now it's pointing here. And we are lucky because it starts after, so it ends up here. And so we go around this loop and we're dereferencing, so we can see this will print out 4, 3, 2, 1, 0. Now, most people pointed out what's unsafe about this. The fact that we have no reference to the start of this array is rather dangerous. If we lose this, we can lose the memory completely, and we won't be able to free it, which brings me to the second question. Someone asked, can we use calloc to free? No. malloc and calloc both need to be freed. Okay? They are both dynamic memory. It's just this memory is 0. So the difference, let's say if I had int star x becomes 5 times size of int. Actually, I'll make it. Let's make it smaller. And if I have int star y becomes calloc 3 size of. So what this looks like in memory, now I'm kind of lying to you a little bit here, but we'll just live with that. Okay. So let's call this 0x4. And we're using a 32-bit system. So this chunk of memory here points to the start of our mallocked or callocked memory, either one. They both look the same. There is one big difference. So we can see we've got 3 times size of int on a 32-bit system, 3 times 4, 3 times 4. The major difference is that in the x case, let's say this is x, this could just be 64 to -5, 7, blah, blah, blah. Okay? The memory hasn't been initialized, so it could be any value. Where in calloc, they're all zeros. Okay? However, we have this pointer to the start of the memory, and either of these cases, we still need to free this memory. Okay? In exactly the same way. And now that pointer is going to be the null pointer, and this memory is free to do whatever it likes. Okay. Does that make sense? Why we need to free both of them? They both work exactly the same, it's just one initializes as the 0. We still need to free this memory. And someone asked, should we increment a copy? Yeah, a copy is a very good idea. A very, very good idea. Another option here, rather than creating a copy, what we could do, so I'll just show you a way we could do this safely without a copy, because I think it's actually a good question. All right. So what I'm going to change in this to make it safe without, if I can find the layer it's on, I'm going to get rid of this. And what I'm going to do is I'm going to change this line completely. And I'm going to go dereference pointer plus I equals x. In the second case, we're going backwards. So I'm going to start I at 4. I'm going to say, well, I is greater or equal to 0, and I plus plus. And then here, I can just go dereference pointer plus I. And that does exactly the same thing, but safely. Okay, because I'm not moving the pointer around. Okay. I'm telling it where to store the memory without moving the pointer. Does that make sense? So let's have a look at that and make sure that it does make sense. Oh, shit. Yep, that should be I minus minus. Good pick up there. Okay, and that does the exact same thing without having to move that pointer around. that.
Actually, this is a good question. I don't know if you did string together. Okay. So have a go at that one. And we'll see what answers you get, or say don't know. Get some answers. Come on, if you're participating. Or don't knows. So string concatenates, meaning it appends two strings together such that string 2 is concatenated to string 1 and the result is stored there. So we end up with the first string is what the hell's happening? The best pizza, new line. The second string is, nothing's happened to string 2.
So it's just best pizza. And then a new one. Okay. So concatenating just joins them together. Okay. Such that string 2 is attached to string 1. Okay. Nothing happens to string 2 though. All right. Are all the people that wanted to know about bitwise stuff here? And bits and number systems and so on. What if there were 3 strings? Well, what do you mean? What if there were 3 strings? Well, give me an example. We can go through it. You can't put 3 strings into string cat. It only allows 2 strings to be in string cat. Yes, it always gets attached to the first line. You have to make sure there's enough space for it too. See how that's got a 15. Okay. So if you had 3 strings, you'd have to do string cat twice if you wanted to add another part to it. If you wanted to concatenate it. Anyone that's in Java, it's just a plus, which makes it a lot easier, but at the same time, conceptually, a lot more difficult. Java's stupid. Yep. All right, where are we? We'll open up a new page. We'll go over some number systems. I'm going to start off very basic. With history. If there's not enough space, you may end up with undesired results. I think it will just try and write it in over memory, which is dangerous. So you may actually segfault. So let's go back to the reason I say that. Yeah, so it should segfault. So let's do a quick example. Where's the pizza? Where'd the pizza go? I've lost it. Okay. So let's have a look at memory. And let's change this to 6. Okay. Okay. 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say. Okay. So let's say the gets stored in memory here. Okay, there's a space, and it's 6 characters. So 1, 2, 3, 5, 6. Okay. So I'm just answering a question in the chat. And then the best pizza, let's say it gets stored here. B-E-S-P-Z. Some more memory. Now, you may end up with multiple things happening. Is that 11? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Beautiful. That's really nice. That's not a 0. Okay. So if I try and concatenate this, what's going to happen is it's going to write the best pizza. Not Terminator. Now, there's two problems here. This could be a legal memory, 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 this could be illegal memory, this could be a legal memory, this could be a legal memory. In this case, this isn't illegal, it's just writing over something you already have, which is dangerous in itself. So it could segfault, it could overwrite memory, could do something bad. And so that's why you need to ensure there's enough space. Does that make sense? Because it may segfault or worse. And what else can happen in this case is that, and this is where I'm getting strange. Let's say this is all legal memory, and I go into A, and then A gets defined here, and this gets changed to 4, let's say. Okay. So you may be able to print out the best pizza, but now you've got this 4 randomly in the middle from another variable. And so this is called undefined behavior. So whenever you're using memory outside of a variable and it's actually running in the program, it may look like it's working, but it's actually undefined and is likely to crash randomly. Okay. So we're going to start off with some pretty simple concepts. I'm going to start off with decimal. Okay. So decimal has deci, meaning 10. Okay. And a decimal system is a base 10 system. Now, for most students coming into university, their whole education and outside of education has been in base 10. Base 10 is very nice. It divides and works really well with human numbers and humans. And so we use base 10, okay? But it doesn't mean we can't use other bases. So let's have a look at base 10 and see what it means. So a base 10 number, let's give an example, 2,000, oops, 2,483. Now, these numbers are ordered in such a way that this is the least significant digit and this is the most significant digit. And each one of these is actually added together. Okay, so we're going back to probably primary school now, but this is a very important concept in understanding other bases. So this 3 here is actually 3 times 10 to the 0. The 8 here is 3 times 10 to the 1. The 4 here is 4 times 10 to the 2. And the 2 here is 10 to the 3. Okay. Now, 10 to the power 0 is 1. 8 to the power 10 to the 1 is 10. 4 to the 10 to the 2 is 100. And 2 to the 10 to the 3 is 1,000. And this is how we define our decimal number system. Okay? And if we add these all up, we get 2,483. Okay? Does that make sense? Is anyone confused about this? And this is really important in terms of understanding binary. It may seem silly that it's so basic, but I'm also going to show you another trick with decimal. And it may help your understanding of shifting. Are we all still here? Where is everyone? I thought we wanted to go through a bit more stuff. Didn't have to. All right. So now I'm going to create another number, which is in decimal. I'm going to make it 48,300. And what I'm going to do is something strange in decimal, but it'll help with the understanding of shifting and the relationship with shifting, and I'll show you in binary how it relates. So I've got 5 places here. Okay. And what I'm going to do is shift to the right 1 place. This gives me 4830. Okay. I'm going to shift to the right 2 places. 483. Okay, given that first number, I'm now going to shift to the left 1 place. So I get 483000. And let's shift to the left 2 places. Can anyone tell me what's happening here? What am I doing when I'm shifting to the right, and what am I doing when I'm shifting to the left by 1 place? And then what am I doing when I'm shifting 2 places and shifting 2 places in decimal? See if you can see the relationship between decimal and what the shift does. If you don't know, once again, say, I don't know. There's no bits. We're not doing bits. This is decimal. So a shift to the right is a divide by 10. A shift to the right 2 places is a divide by 100. A shift to the left 1 place is a times by 10. A shift to the left 2 places is a times by 100. Okay, so we can see that relationship. And this relationship works in all bases. Okay, but it's not 10, it's whatever base it is. Okay. Does that make sense? So we end up with times 10 to the n amount of places, or divide 10 to the n amount of places. So we can apply some maths to do some different types of shifting with decimal. Okay. So with our decimal number system, our base 10 number system, we have 10 digits. And these digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now with this, when we're counting, 5, 6, 7, 8, 9. What happens when we get to this 9? I know this is an easy question, but it's an important question. A lot of people here, but there's not much interaction. I'm disappointed. What's that? Yes. So we carry, and we end up with a 1 in the tens, and we end up with a 0. Okay, and so we keep counting. And this will all follow the same rule. Okay, and we'll see that there is a pattern. So we'll have our digits, our digits, our digits, our digits, our digits. Okay, I think you should know this by now. So if we go to another base, let's say, base 8. Okay. So base 8, we now only have 8 digits. Okay. And if I have the number 217, this number follows the same rule as before. So we have 2 times 8 to the 2 plus 1 times 8 to the 1 plus 7 times 8 to the 0. Okay. And it also follows the same rule in, if I have 217 and I shift it 1 place to the left, then that's a times by 8. If I have 217 and I shift it to the right, that is a divide by 8. It also follows the same rules, and there's lots of other rules as well. But These are the basic ones which concern you. If I count up, 6, 7, what do I do now? What do I do once I reach 7? Come on, guys. Use the chat. It is really annoying talking to yourself. So spam it, do whatever, make jokes, whatever. I don't care, but just interact. Yeah. So you get 1 in the 8s and 0 here, and then you keep counting. Okay, so we've got this system down. So if I go to base 5, you should be able to count in base 5. If I go to base 3, you should be able to count in base 3. If I go to base 263, you should be able to do that. So there's 3 systems that we really care about on computers, and there's 3 that we really care about, and often 8 is also helpful, right? Isn't very often, but some people do, if you like it. Now, base 16, same thing. Oops, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now what do we do when we get to the 9? Yes. Actually, so someone asked a question, which is the worst thing that could possibly happen to you. And it did actually happen to a class where it was in humanities. And they did show the exam. And they had to do a resit later, and the exam had to be rewritten. And it was off schedule. So, yeah, the exam getting out is really bad for both, obviously, whoever showed it, but also the students, because they have to resit the exam. And they probably have to sit 2 exams and get 0 for the first one. So, yeah, it's not a good thing. Anyways, so it's not carry, but it's just add. C, D, E, F, and then you carry. Okay, so that's base 16. What do you need to study for? I don't give you my time now. No, it's really not a good thing to happen. There was another exam recently this semester that got pulled because the answer sheet was in the exam. I heard about that, like I think it was last week when it happened. And the students all got 0 for that exam, and they have to reset another exam. Whoever did that is an idiot, but yeah. So base 2, same thing. We go 0, 1. There's no more digits, so we go 1, 0, 1, 1, 1, 0, 0, 1, 1 0 0 1 1 1 0 1 1 1 0 0 0. Yeah, I'm not joking. It's kind of funny if you think about it. All right, so counting up in binary, you should be able to do it. Now there is obviously a pattern, as there is a pattern with decimal. If you want to memorize the pattern, you can, but you should all be able to count up. If you can count up, then you understand what you're doing, meaning you can quickly put this table together, but also understand it. Now there is a really nice relationship between base 8, base 2, base 16, base 32, base 64, base 128, base 256, base 512, 1024, 248, and so on. And I think I've seen a base greater than 256 though. I think the highest I've used is base 64. That's a pain, because you literally run out of characters to use. All right. So this is a table you should write down, which will help you quite a lot in the exam, to quickly convert between decimal and binary. Yes, so I can show you an example of where a big base is applicable, and it was something that I did recently. So this is the table that you should write down on the back of one of your exam pages once you get in, and I'll show you why in a second after I answer this question. So let's say I had the 8th of the 10th, 2017, 6 hours, 15 minutes, 32 seconds, 84 milliseconds. Okay. So this number as text can be compressed. Now this is a date and time. By using a higher base, I can compress this down to a lot smaller number. Yes, I can. I think Bo might have put an incorrect answer, well, explanation on it. I think he did. Someone emailed me about that. All right. So we have all these numbers, and we have all of this. Now, why is this good? This is base 2, and this is base 16, or hexadecimal. Okay. Now, you should be able to convert between both of these very quickly and easily. Okay. Now, as long as you know these, you don't need to know any higher because of the nice conversion between the two. So if we pull up these, and we get to bitwise. So I have to make some new ones. I'll keep my table. I'll take my table and run. No. Okay, so I've got the table, which, all right, so I'm going to create some hex to binary and some binary to hex questions. So we go 1 0 1 0 1 0 0. If a 1 0 0 0 0 1. Actually, not really 0 though. Let's see. 8 0 0 1. A, B, C, D. And then we're going to go from binary to hex. So I'm going to go 1 0 1 1 1 0 1 0 0 0 0 1 1 1. I'm going to go 0 0 0 0 0 0 0 0 0 0 1. I'm going to go 1 0 0 0 0 0 0 1 1 0 0 0. And I'm going to go 0 0 0 1 1 1. And I'm going to go 1 0 0 1 1. And I'm going to go 0 0 0 1 0 0 1. So I want you to convert these numbers into, let's go as A, B, C, D, E. Let's do this 1. Let's call this A, B, C, D, E, F, G. So I want you to convert these numbers into hex. I want you to convert these numbers from hex to binary and these numbers from binary to hex. So have a quick go at that and then we'll go through them. And yes, we'll get to question 10. But I want to make sure that you understand the preliminary before you understand that. Because if you understand this, question 10 is quite easy. You've seen notation. So just before we go with that, 0x, 0, 1. This is specifying a integer hexadecimal literal. And 0b, 0, 1 is a binary. And 0, 1, 0, 1 is octal. 1 is decimal. Now, this notation is purely for code. Generally, in mathematics, you'll write, let's say, A, and you'll put a 16, or A and a H there. In base, let's say 8, you put an 8 there, or you put O for octal. For decimal, so if I have 92, you put a 10 there, or you put a D. And for binary, you put 2 there, or you put a B there. So that's the mathematical notation. This is the notation for C, and depending on what language you're using, the literals will be specified in different ways. the notation is purely to indicate a literal. So 0x is a literal for hex. 0b is a literal for binary. Right, go and do that. I'll be back in 2 seconds. And I want everyone to attempt it. Okay? If you don't know, say don't know or make a joke. Okay. So this you need to know, because it basically limits you from answering a huge amount of questions, including question 10 in your exam. And you need to know how to do this conversion. It's really, really, really important. So let's go through them. It is not hard, and it should be very quickly, and at this stage you should be able to do it very quickly. So, I need some room. If I can, let's do these one at a time and delete them. All right, so let's look at this first one. So going from hex to binary, and this is why the relationship is really nice and why the conversion is really nice. So this is a hexadecimal number, and we want to go from binary, so we're going this way. Now, with hex to binary, each digit just becomes 4 binary digits. So this 0, if we go to our table, 0 becomes these 4 zeros. Now, as I said, this table won't be on the exam, you need to know it. Okay? 1 becomes 0, 0, 0, 1. 0 becomes 0, 0, 0, 0. 1 becomes 0, 0, 0, 1. 0 becomes 0, 0, 0. 1 becomes 0, 0, 0, 1. 0 becomes 0, 0, 0. And 1 becomes 0, 0, 0, 1. So we end up with 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, and I've already lost where I'm at. 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, now it's quite a long number, but you should be able to convert it. It shouldn't make a difference how long the number is. Does that make sense? Does that one make sense? Okay. So if you can't do this, you will be very limited in the exam. And there is no cheat sheet for this. The only thing that's given is the precedence table, which is your order of operations. Are we happy with this? Yes, no, funny joke, etc. Also, I like that joke. That was good. Okay. All right. The next one, we have FE 1, 0. So 0 becomes 0, 0, 0. 1 becomes 0, 0, 0, 1. E is down here, so we get 1, 1, 1, 0. And F is 1, 1, 1, 1. So we should be able to do that conversion very quickly. Now, someone asked about grouping them. You can group them however you like. Generally, programmers like to group them in 8s because that's the size of a byte, or in 4s because that's the size of half bytes. You can group them however, you don't have to group them at all. You could just write 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Grouping is kind of like in decimal,
because we all like talking about decimal, we'll see people write this comma here. It is the exact same thing. You don't need the comma, but it makes it look more readable. Okay, so if I have a million, I write it like that rather than like that, but they are both correct. The same here. If I decide to group them like this or this, it's still the same number. It's just, it's more readable if we group them into 4s or 8s. Okay. But it doesn't change the answer. Okay, does that make sense? It's a good question, though. Okay. This next one is an interesting one. Now, because I haven't specified the size, and we're just converting numbers, this here is 1. Okay? Because it's zeros in front of it, in binary it's 1, in hex it's 1. These are just leading zeros. So if we go to decimal, and I have the number 428, and I add a 0 in front of it, it's still 428. If I add another 0 in front of it, it's still 428. Same thing here. So I could write 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, but in reality it's still 1 in both binary and hex. Okay. The next one we have is 8001. Now this one we can't. So here we have 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay, and you can see that we've got a nice symmetry there. Okay. Oops. And the last one is A, B, C, D. So let me just write this up here, A, B, C, D. So 1, 0, 1, 0, 0, 1, 0, 0, 1. Okay. And so once you get used to it, you can write these and flip them between each other fairly quickly. Okay, are we all happy with the hex to binary conversion? You need to know. Okay, so now we're going to binary to hex. Now, this is very similar, but we're going the other way now. And if you have your table, we can quickly convert between them. And this is done by grouping them in 4s and just going backwards. Okay, so we can just group these into 4s. And 1101, we can look up on our table, it should be D, and we can go 1011, look up on our table, it should be B. So we get BD. Okay, we go to this next one, and we group them. Now these are all zeros, and they're leading zeros, so we can kind of ignore them. We get F. Okay, if I put a 0 in front of it, it's still the same number. Okay, it's still 15 in decimal. All right, so we've got them ones done. All right, so what's the next one in hex? Give me an answer.
It should be a fairly easy one. What's that? Yeah, it's just one. Okay. Right, what about the next one? Okay. So with decimal, with hex, with everything, we always read this way. So these zeros are the start of your number. Okay? So we get a 0 here, we get a 3 here, we get a 0 here. Now, there is a 1 here, but we can just chuck in some zeros to make that a 4, like a group of 4, and so we get a 1. And so we get 1, 0, 3, 0. Okay? That's perfectly fine. It doesn't have 13 bytes, it has 13 bits. But we're just talking about number systems right now. We're not even talking about bits. We're just converting numbers. It's not bits. It's not bytes, it's bits. Okay. This is irrelevant to, this is just maths at this stage. There's nothing to do with programming just yet. Well, that's something to do with programming. But, so this one here, same thing. We have 7. Here, we have 7, and we have a couple of extra bits. So we have a 0 and a 0 there, just to fill them in, because as I said, we can add zeros to the front of numbers. Perfectly fine. And so here we get a 2. So we get 2, 7 in hex. And same with the last one. You'll notice the last one is a 0 at the start. So we just get 2, 7 again. There's no need to add the extra zeros in the front. There is, once we get to thinking about it in terms of memory, but at this stage, because we're just looking at the maths, the zeros don't mean much. All right. So now what I want to look at is let's say I have this number 1, 1, 0, 0, 1, 1, 0, 0. Now, you are not expected to convert from decimal to binary, binary to decimal in the exam, but as we saw before, we have the same concept. So if you want to do a quick conversion to check your answers or something like that, you can. I'm going to run out of room. I'm not make this longer. So we have 0 times 2 to the 0, 1 times 2 to the 1, 1 times 2 to the 2, 0 times 2 to the 3, plus 1 times 2 to the 4, plus 1 times 2 to the 5. Now we can ignore the zeros because obviously anything times 0 is 0. Times 2 to the 1. So 2 to the 1 is obviously 2. 2 to the 2 is 8. 2 to the 4 is 16. 2 to the 5 is 32. So, sorry. So we get 54. Okay. So if you want to convert to decimal, that's the way you do it. Now, going from decimal to binary is a little bit more difficult, and you do that for division or remainder, but you're not expected to do that in this exam, so don't worry about it. Okay, does that make sense? Now, I'm going to do one thing. I'm going to binary to hex and hex to binary. You do need to know 100%. Okay. So not just binary to hex, but hex to binary as well. Okay. So what I'm going to do right now is I'm going to shift this one place to the right. What value in decimal will it be after I shift it? So let's have a look. So if I get 0, 0, 0, 1, 1, 0, 1, 1, okay, so I've shifted one place to the right. Then I get 1 plus 2 plus 8 plus 16. Okay. And we get 27. Now, what did I do? 54 divided by 2. Okay. Is 27. So we just proved that shifting to the right is divided by 2, which makes sense because it follows our rule that we had somewhere up here. And so we've gone full circle. And so if we shift to the left, we times by 2. Okay? Does that make sense? So with shifting, we are timesing and dividing by 2. And that's quite a powerful thing when it comes to computers, because computers can times and divide by 2 incredibly fast. And this is why memory is always 128 and 256 and all that. Obviously, it's because it's a multiple, but because also we can do these incredibly fast calculations because of this. We can shift stuff around. All right, so now we'll go to the memory level and we'll start moving stuff. So we are we all comfortable up to this point? Is there any questions? All right. Are we all good? We're all good with binary and hex in terms of the maths. And now we'll go into the computer side of things, if we're all pretty good. Are you ready? Ready to understand the truth about binary? How long am I planning to stay? As long as people keep talking, I'll stay for a while. If it goes quiet, then I'll leave. It's basically, I'll run this. Yeah, as long as there's lots of comments, as long as it's not boring. Yeah, more comments, and it doesn't have to be serious comments. You kept asking about question 10, but you didn't understand how to convert the numbers, so question 10 is still a little bit away. We're getting to question 10. We need to understand everything before that. All right. can't I get it? The question was, is there a difference between the bachelor's and master's? Yeah, it's longer, and there's an extra question, but it's still the same percentage. So you have to be careful because it is not an easy question. The format is pretty much exactly the same. The questions are different, but the format's exactly the same. Minus the practice exams printed on one-sided, where the exam will be printed. I mean, the practice exam was printed double-sided, where the exam will be printed one-sided. But the format will be the same. All right. So now we're going to look at binary and bitwise and fully understand bitwise so that we don't have to worry about it ever again. And then we'll go on to some other stuff, which will be fun. So I just put a picture up there. That's a mechanical decimal computer. Now, we are lucky that computing's gone far. We decided to not stick with the decimal system, but rather the binary system, because we then need decimal states. And for those that are doing engineering, they'll learn about transistors and the fact that we can have an on and off state in electronics quite easily. And so memory, rather than having big rings that go from 0 to 9, that are fairly mechanical, we can use electronics to basically have states of on or off. Okay. Now you also learn that there's actually 4 states in electronics, but we don't care about that. And we don't care about supercomputers. I mean, not quantum computing either. All right, so we have a 1 or a 0. And these are on or off states, true or false states, whatever you want to call them. And on a computer, in memory, in your RAM, in your hard drive, etc., they'll somehow be on or off. So, and same with other digital media, say DVDs and stuff like that. And the on-off state on a DVD is basically if it's reflective or not. When on a hard disk, it's if it's magnetic or not. It's on or off. On RAM, we've got caps. You've got a similar situation. So your memory on whatever device, we can imagine it as being zeros and ones. Now, it's not really a 0 or 1. It's some electric charge, it's some magnetic strip, it's some shiny bit on your DVD. It refracts the light from the laser differently, depending on if it's a 0 or 1. Okay, so we treat that as zeros and ones, but obviously in the real world, they aren't actually zeros and ones. It is just an on-off state. So in memory, we have a bunch of these, and they're just in order. And so on. Okay. And so each one of these is called a bit. Okay. And a bit can have two states, 0 or 1. Now, like this, they don't have much meaning. So we group them into 8s. To create a byte. Okay. And each byte in memory has an address. We can then group them further to do other things, like let's say an int or a short or something like that. But for the computer, all it cares about is that they're stored in bytes. For our program, we can treat them bytes differently. Okay, are we happy with that concept? Questions? When do we get to learn the dark side of coding? Depends. Maybe tomorrow. Do some dark side of coding. Okay. So now we are going to go and have a look at bitwise operations on a computer. So first things first, if I have int actually, no, it's actually a very good question. So I'm going to store 52 into memory. Now, I'll copy this. So that you have a reference. So this is more of a deeper understanding. But on our Unix system, which is a 32-bit system, now one thing you may be aware of, when I say 32-bit system, I'm kind of being a little devious, but there's so much to computers nowadays that we can't explain everything. We have to kind of be a bit devious. Tell me how this is stored. How many bytes? Which order? Etc. Etc. Take a couple of minutes to think about the size and how it's stored. Now, how it's stored is a little bit further than what's covered in the subject, but you have done it, I think, 3 times already in this subject in the labs. So give it a go.
All right. How we go? I'm not getting as many answers. Okay. So just remember, and this is for future, not now, but remember Little Indian. So the data is stored like this. Okay. However, that doesn't affect any of our bitwise operations. So we can treat this as being in big Indian for all our operations, and we will. Okay. So I just want to get that point across so that no one gets confused about that. So in memory, it is stored backwards in Little Indian, but that doesn't mean that when we perform our operations that it looks like this. Okay, the operations are still performed normally. Okay, so now let's have a look at the operations. So I'm going to create another variable. I'm going to make it a short, so I like shorts. I'm going to make short x, and I'm going to specify. Let's specify 0x01. Then I'm going to go short y becomes 0b 0 0 1 1 plus x. So here we've got quite a simple sum. We can see that this is decimal 1. We can quickly see that this is decimal 3. So we end up with y having 4 in it. Okay. So whatever way we want to store it, that's perfectly fine. I mean, we want to interpret it, that's fine. But we have to remember that this is a short. Now I'm going to treat everything as big Indian after that question, just so that we can understand what's happening. And so y now has 4 in it. Okay? And that's what it looks like in memory. Okay, so these leading zeros are there in memory now. Now that we're not dealing with maths, we're dealing with actual memory, there are leading zeros. Okay, because they can't be nothing unless we physically rip out the memory. So what I'm going to do is now basically play around with this. So we're going to apply some shifting first. So if I go y becomes x, actually let's go the other way around. So this variable here is y. I don't care about x because I'm going to. I'm going to go y shifted 1 place to the left. Okay, so this is to the left. So this is y shifted 1 place to the left. So we already know from our maths that the result will be 8. But in memory, we are shifting 1 place. Now you'll see that a 0 gets introduced and this last 0 gets popped off the end. Okay. Now with shifts, we just introduce a 0. Okay. So my question to you is, if I have x, y shifted 4 places, what's the value in x? And please answer because the chat is starting to die. So it's going to be boring. Okay, so we're all able to see very quickly that it becomes 0. So every one of these moves across 4 places. The only digit here is a 1, so this moves across 4 places and we get 0. Now let's shake this up a little bit. Let's change x to be 0x 02 shifted 2 places, shifted 2 places, shifted 2 places, and shifted 2 places. Now this you should be able to do instantly if you see what's happening. What's in x? In any base, just tell me which base. Okay. So does anyone not understand why that's still 2? Okay, I think everyone understands that. I'm getting lots of answers. Okay. So what about if I had 0x 02 shifted 0x 02 shifted 0x 02? Well, what would I get now? This one's a little bit more difficult. Give me a minute to solve that. The whole button of my sheet. It's some really interesting answers. One person's got it. I'll give a couple of minutes more with everyone else. 16 in what base? Base 10? I don't even know what base. Base 43. You're going to say 16. Tell me what base. Okay. So let's have a look at this. So what I'm going to do first is let's just convert this number here. No, I don't really care about that number, that's not in brackets. Let's convert this number to binary. Now, this is 2 bytes long, but I'm just going to do 1 byte for now. So I've got 2, and I'm going to shift this 2. Okay, so I get 1, 2. Okay. Now, this here is 2. Okay. But what are we left with? We're left with this number, which is what? So we can quickly do a conversion from binary to hex and go 0x8. Okay. And going from 8 to 8 in decimal is just 8. So we have 8 here. So let's get rid of that. Let's get rid of that. Let's just rewrite it as 8. So we have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, shifted 8 places. Now 8 is a whole byte, so it's just offset by a byte. So we're going 1, 2, 3, 4, 5, 6, 7, 8. And we'll notice that the byte is just shifted up 1 place. And so there was one person that got this right. So we now end up with 0x to, oh, I'm going to actually do the leading 0 just because it is a short 0. Okay. I got it right. Okay. All right. So we're all pretty good at shifting now. What if I had something? No, I've already seen that. All right. So that's shifting. Okay. So shifting's fairly easy. Now, what we want to look at quickly is the ORs, the ANDs, and the XORs.
Actually, what I should do is move that over to 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1. Now, these are not conditional. Okay, these are binary operations, and I think most people are pretty good at them. So, okay, so you should know how to do this for your exam. You should know this table. No, it was a short. Short is 2 bytes. So you should know definitely or either have to be true or both, and they both have to be true. XOR, they either has to be true but not both. And I say true, but it's on. We're not talking about conditions here, so just be careful. All right, so let's do a quick example. Int x, let's do short x is 0x, actually, I'm doing int. F2 8a 0 0 0 0 and 0x 0 0. Actually, 8 4 3 2. Okay. What's the answer to this? Go. Should take you 2 seconds. So I'll add a couple of other ones there for people who have done that one. Now these are not very calculation based, they're just conceptual. Because there isn't really much calculations in these ones. Why did I choose ints? That was stupid. Okay, so have a go at those. There's 6 there. They shouldn't require any calculations to solve them. You should just be able to look at them, work out the answers. If you don't know, say you don't know. Give it a couple of minutes or so. Who wants to can try it. And if you all say you don't know, then we'll go through it. But just a clue, there is no calculations needed. Okay, we're getting some answers now, which are looking pretty good. So for those that don't understand, let's go through it and just look at it conceptually. So I might step back a step and we go back to these, and we'll come back to these a little bit later. So what I'm going to do is just have a look at something more simple. So I'm going to go int x 0x 22 ANDed with 0x 7 4. Okay, so we can quickly convert these to binary. So we get 0 0 1 0 0 0 0 7 0 1 4 is 0 1 0 0. Now with an AND, a bitwise AND, we are doing an operation between every bit. So we take this 0x22, which is 0 0 1 0 0 0 1 0. We take this 0x74, which is 0 1 1 1 0 1 0 0. And we know that they both have to be true for this to be true. So these are both zeros. That's a 1 and a 0. That's a 1 and a 0. That's a 0 and a 0. That's a 0 and a 1. That's a 1. That's a 0. That's a 0. And we can convert this back. So we got 2 0. So we know x has 0 0 2 0 in hex stored in it. Okay, it's actually int, so okay. Does that make sense? Okay. So we're doing that bitwise between every single individual one. Okay, so if we change this around, and we do an OR this time, so let's make this an OR. Now we are comparing if either of them are true. So we've got a 0 and a 0, so we get a 0. A 1 or a 0, so that's a 1. A 1 or a 0, so that's a 1. A 0 and a 0, so that's a 0. A 1 and a 0, so that's a 1. A 1 and a 1. A 1 and a 0. So we end up with 7, 6. Okay? So that's our OR. Right? And we're doing it bit by bit. Now there is one other operation which I forgot to show you, but we'll come back to that. And this is an XOR. So this is 1 if either of them are a 1, but not both. So 0, 1, 1, 0, 1, 0, 1, 0. So in this case, we get 5, 6. It depends. Most questions wouldn't ask you so if a question asks you for a value, you could either put H here if you wanted to specify it in hexadecimal, or you could put 0x, or you could change it to decimal or whatever. I doubt a question is going to ask you that. More likely it's going to have a printf statement. But if it does, yeah, just however you want. All right. So does that make sense? Then 3 operations. Just say yes if they do. Yeah, I think most so the ones that will, yeah, so it's actually a good question. So the ones that it's the same format as the practice exam. So the only ones that will ask you a value is going to be in the multi-choice, because the second ones are the printing ones. So that'll be the printfs. So it'll give you the format. So yes, there will be formats, but it will be in the multi-choice. And I can't remember how they've written that. All right. So now we go back to this. And there is no calculations here needed, because we should be able to see that we have x here, and we have this, we have this 32-bit number. Now, this is also a 32-bit number, but it's missing the zeros from the front, so we'll just add them in. Now, 0 ANDed with anything, so if I have 0, 0, 0, any number I put here, if it's 0, 1, 0, 1, or if it's 1, 0, 1, 0, or if it's 1, 1, 1, 1, it's always going to end up as 0, because 0, 1, 0, 0, 0. So we can see here that 0 and 8 is going to be 0, 0 and 4 is going to be 0, 0 and 3 is going to be 0, 0 and 2 is going to be 0, and these front zeros are the same. So x comes out to be 0x, 0, 0, 0, 0, 0, 0, 0, 0. We should also be able to see the relationship that if we have the same number ANDed, so if we have 22 here, that number added together will just be the same number because they're both ones. So this number here in y is going to be F28A1738. You can see I don't need to do any calculations here. Now the OR, if I OR anything with 0, we can see it's a 0, 1, a 0, 0, a 0, 1, a 0. So we end up in this case with a 0, 1, 0, 1. In this case here, we end up with 1, 0, 1, 0. In this case, we end up with 1, 1, 1. So it just retains its value if it's ORed with 0. Now this is really helpful with that bitwise operations a little later. So here we have a bunch of zeros, here we have a bunch of zeros, so we end up with A1, 2, 4, 1, 1, 8, 3. Okay. Anything ORed together, okay, with itself, so if I put an OR here, a 1 or a 1 and a 1 or a 1 still results in the same value, so we end up with the same value again. So 428A1738. Okay. The next one here is the XOR. Now, as long as they're different, they will change. Okay? If they're the same, they won't though. So a 0 and 1, a 0, 0, a 0, 1, and 0, 0 will still result in this 0, 1, 0, 1 because it's not a 1 and a 1. So in this case, we end up with A124, 1183. Okay? And in this last case, it's very different. So if we exclusively OR this together, we know that our rule with XOR is this 0 here if they're both true. So we actually end up with zeros when these are XORed together. So anything XORed with itself will end up with zeros. Does that make sense? People are starting to pop off. Most of the people here are in good school anyway. All right. So I want to present an interesting let's say in B. I don't know. We'll get to it. I want to make sure we understand everything before we jump to it. I've been over this bitwise stuff so many times. It's a huge part of the exam. So I just want to make sure it's all good. Let's let's do something different. Let's do something. A2. R2. All that. Okay. I'm gonna have a quick break. We'll be back in 5 minutes. Have a go at that. So this has the not operator in it. And you have to be very careful with the not operator. Okay. I think it's been about 5 minutes. Which is good. Alright, who's still here? If you're still here, put a big smiley face in the chat or something. And we'll go through this question. If you've got an answer, chuck it in the chat. And then we'll go through the rest of bitwise. And I think we're done with bitwise. That's not a smiley face, it's a sad face. You should be excited. You've got an exam coming up. Programming. How fun. How much fun. Okay, so let's have a look at this. So we have 0x, a2, 0, 0, we have more, we have the not, and we have a. Now this is a binary not, so it basically is an inversion. So we have here an int, which, as we've said, we're assuming 32 bits, because that's what we're using in our systems. So we have 0, 0, 0, 0, 0, 0, ff, and we want to flip that. So we get f, 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 0, 0. And we're going to OR that with 0, 0, 0, 0, a 2, 0, 0. Now, f is 1. So anything ORed with a 1 will be true. A 0 or a 0 will be 0. So B has f, 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 0, 0. Does that make sense? Now you have to be careful with the inversion. Because of this reason, it does depend on the size, and it does depend on the size of the system as well with literals. The literals will be treated as 32-bit here, unless you try and apply the operation between something smaller, such that it casts it down. Oh yeah, I had that interesting question. So I might go on to just quickly go through one of the questions on bitwise that was asked a couple of million times. And I've got all the tools that we need to deal with it. I'm running out of room. What is the question? Question 10. So I'm just going to get this question up. Someone was asking about it earlier. think they've gone. So here we have our bitwise operations. We also have these standard bitwise operations to do particular tasks. So we have the set, clear, and so on. You can actually be a bit more creative with these, but we've limited them to the simple ones. So if you're able to, you would be able to pick up that that's a toggle from your labs. But if not, we'll go through it the longhand way just to make sure that it sinks in. So 5, we should be able to convert to binary fairly quickly. Anything under 15, you should be able to convert from decimal to binary fairly easily. And we've got 0. Now these are unsigned. There should be an int there. You'll get a warning. This will actually compile. It will assume that there's an int. That's strange. That I did not write this. It's weird. I thought that came off the quiz. That's interesting. I have to check out the quiz. All right, so we've got lock equals lock odd with 1 input. Now, there is implied brackets there because this has to happen before this to make sense. So we have lock, which is 0, 0, 0, 0, 0, 0, 0, 0. And we have 1 shifted input amount of places, which is 5. We don't need to know that in binary. We do need to know this one in binary though. So we have 0, 0, 0, 1. And we're going to shift this 5 places. 1, 2, 3, 4, 5. And so we end up with 1, 0, 0, 0, 0, 0. Okay. I don't really care about the zeros in front of it. And we're going to XOR this with this. And so we end up with a 1 here. Now, we quickly can group these into 4s, and we get a 2, and we get a 0. And so we can see. Does that one make sense? So I think, did one of you ask about string functions earlier? Or if that person got? Which string functions do you need to know? Grab the list. Personally, I would say none of them. But for the exam, I need to know some. I don't really like this string library. It's too slow. There's better ways of doing stuff. Okay. It's like a pen. Actually picked up a real pen. So you need to know. Ugh. String lengths. String QP. String. I think that's it. I think. No. Should probably know string copy. String compare. They're the ones that are on the lectures. These are the really important ones. I'd probably keep string cat in the back of your mind as well. I'm not sure if it's on the exam or not. But yeah, these are definitely, especially the compare one, and length, they're very important. But I would probably know all those. All right. So I think I've got. I think you guys are going to go very well in the exam. So I'm wondering if I can pose a question to you. Let's see if you can stop me. It's quite an interesting question. And not to be mean, it is a difficult question. I posed this to the other demonstrators and they weren't able to get it, but maybe you can. It's a really good question. But it is conceptually difficult. But all right, so I might come back to this. So I've got a question now, but I'll come back to it once I answer that other question. So string compare and string n compare. So most of the string functions will have both an n version. So this string n cat, this string n string, this string, and so on. The string n copy, the string copy. And there is a reason for that. It's purely for safety. It's actually a really good idea. So string compare has the prototype int string compare. I think it's a const. I don't think this is right. It doesn't sound right. I think lecture notes are wrong. that should be a const. And I'm sure, yeah, it is. Electronauts are wrong. It doesn't really matter that this is a const, but it matters to me. Because it wouldn't make sense otherwise. I don't know why I didn't include that. So string compare has this format versus string n compare, which has this prototype. Election notes are dodgy. All right. So your election notes will have something slightly different than this, but this is the actual prototype. And I prefer to show you the real one. Because then you can learn about these things later. Right. So string compare and string n compare work very similar, but they are slightly different. So I'm going to introduce 3 strings. So let's say car A, let's just say 10, I don't know what I'm writing. Let's just say 20 just in case I just know, so like to my right. All right. Okay. I'll see. Right, C is fun. C is fun. All right, C is super. So that's what you're thinking. So we remember that string compare returns 0 if they're equal. So I'm going to go, I'm just going to make a variable, not A obviously, so that would be stupid. So I'm going to go X string compare A and B. I'll go X string compare A and C. And I'll go X string compare. And I'm overriding X. Well, I don't really care. So what is X at this point? What is X at this point? And what is X at this point in the program? This is my question to you. String. So everyone put their answers. just to make this interesting. Cool. So just remember that if they're equal, it does return 0. Okay. So you had it around the wrong way. And it doesn't actually return 0. It will return, remember, less than if it's less than, or greater than if it's greater than. So what I'm going to do now is I'm going to look at string n compare instead. And I've just added another one to make it more interesting. And we'll have a look at that case because I think that will make sure that some of the better students understand this well. So string n compare, string n compare, string n compare. I'll go A with B, and I'm going to compare, let's just say 4. Okay. So which one's true and which one's false? Which one? Sorry. What is X at the different points? So give us your answers. Okay. So we can see that we've got a pretty good understanding there. Okay, these are correct. Now I'm going to do one other thing, just to shake things up a little bit. So I'm going to go car star E is D plus. Oh, you didn't understand it. Sorry, I thought you understood it. All right, so string n is just looking at the first 4 characters. So 1, 2, 3, 4. So A and B, when we just look at these 4, they're equal, so it returns 0. A and C, the first 4 characters, they're the same, so they're equal. And yes. All right. So I'm going to look at one more case. So I'm going to go cast E is D. When it's greater than. So if we swip them around, basically, it just has to do with the letters and their ordering. You can knot it. Or you can just check if it's 0. It's up to you. It is kind of against convention, but string functions are silly. So now we're going to have to compare E, C. I'm going to go 5. What value is X now? Get up. There is something. So E is a pointer, and we remember D points to the first thing in the array. We add 9. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. That didn't count correctly, but it doesn't matter. That's still good. Now, that's not what I wanted to do anyway. Now we're comparing different places in our array. Okay. So we're just comparing here and here. So we can use pointers to look at different positions in our array with our string functions. Right. Right. So someone asked about another question. This one shouldn't take long. This one's very easy. All right, so this is another bitwise one. We should all be pretty good with bitwise now. So we've got 3, which we know in binary is 0, 0, 0, 0, 0, 0, 1, 1. Now, we've got this and equals here, and we've got this not 1. Now, we could go about this a couple of ways, but we can also see if we wanted to, this is up to you, but we can see that this is exactly the same as bit test and not 1 shifted 0 places. Okay? Because 1 shifted 0 places is obviously 1. So we can see that we're clearing the first bit. But if we want to do this longhand, we can. So bit test is, so we've got bit test and not 1. Bit test is 0, 0, 0, 0, 0, 0, 1, 1, and we're ending that with 1, 1, 1, 1, 1, 1, 1, 0. If we add them together, just changes that to a 0, which we expected. So we get 0, 0, 0, 0, 0, 1, 0. We convert this back to hex. We get 2. So bit test has 2 in it. We then do this comparison here. So we're testing. We're testing if bit test has a 1, or we can just go through this. So we can go 0, 0, 0, 1, 0, and with 0, 0, 0, 0, 0, 0, 0, 1. Now, here we end up with 0. Okay? Now, we aren't comparing if it's set, we're comparing if it's cleared in this case, because we're comparing with 0. And 0 is equal to 0. So this is true. Now, we can quickly see anything ANDed with itself, as we saw before, will result in itself. Okay? And we know that bit test has 2 in it, so 2 and 2 will give 0x02. So this can't be true. We don't even need to check this. So it prints 2. Does that make sense to the person who asked? Or is there a step? You look like we're covered. Look at that mistake. They should blow that up. Where's my... Does that make sense? I know someone asked that question. Right. We're gonna have a little break, and then I might come back to a problem, a fun problem. Unless there's something specific that you want to ask. Yeah. Yeah. I'd like to go through something a little bit more logical, because we didn't get to go through much logic this semester. Very quick break.
Sleep? What is sleep? Come on. I want you guys to fill this exam and make sure of it. Alright. So, before we finish, I thought I might pose a question. This isn't going to be an exam, but it's good to understand how things are executed in C and its implications. So I've got this little bit of code here. And it's all stuff you've done before. But it's a mistake and a problem that a lot of people do. And firstly, I just ask, can you see what the problem is? And there's multiple problems here. Figure them out. No, so do something with CH means that there'd be something inside there. I'm not worried about that. So we have this special macro for end of file, okay? And we've seen this before, and I believe we've used it before, and it was in the lectures, okay? Now, I'm curious to see. I just did the this is quite a big problem in experienced programmers. I just want to see. Okay, so I'm going to type something in the chat. That's all right. Sweet. See you then. I think it's uploaded to the exam tab. Okay, so this problem is actually something that's commonly done, and it's a very easy mistake to make, especially when you understand C, but you don't really understand the full context of it, and how things are converted, and what this ELF actually means. So most problems can be solved with C, even if you're not so good. But you end up with this very common bug. And the reason that this is something I want to bring up is because it's really common, especially people that haven't done a lot of reading on C and how it works. Now, I'm going to give some context here. So, car, firstly, is defined as 8 bits in the C standard. Okay. However, it is the only type that isn't defined if it and this is getting quite deep into C, but this is something that I enjoy reading about. I'll show you some stuff tomorrow, which will add some more context to what you're doing. So all of your other variables except for car are defined as being signed, okay, in the C standard. However, car is not. No, this is definitely not on the exam. Like something like this might be on the exam, but it'll be wrong. Like these concepts might be on the exam, but this actual example isn't. I just find something's funny. All right. So it's not defined as signed or unsigned. So this means the compiler decides. Okay. GCC decides that it is signed. But if you run it on a different compiler or you change the compiler settings, you can choose to make it signed or unsigned. It's up to you. Okay. So that's the first important thing. The second important thing to note, which is something that a lot of people miss, but it is actually quite critical. So if you look at your functions like get car or get fget C and so on, you'll notice that their prototypes don't return a car. They actually return an int. Okay? And this is quite important. Okay? So these return an int.
Now, we know that the ASCII characters are all car. Okay, they're not int. So they're all 8-bit. It's going to be available on the exam. It's on the exam tab, not the live stream tab. So they're all 8-bit. So it's kind of strange that it returns an int. Then we have a look at this end of file, meaning you've reached the end of file. Now, it is important to understand that this is not a character. It is a code. So the value of this is 0x ff 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 ff. Okay. So we can see already that this here is not a car. All right. So let's look at two cases. Now, a couple of other things to understand, and this is why this is fairly complex, but I don't want you to make the same mistake that a lot of people make. So 0x f f f f f f f is -1 in decimal if it's signed. Okay, so just be aware of that as well. This is kind of important. And 0xff for a car, so that's if it's an int. If it's a car and it's signed, then it's -1. Okay. Otherwise, it's 255. So we have this f gets c from a file, and we get some characters, and it returns an int. Now, it can get all of these characters. It can also get this end of file. But the problem here is we have this car C that has to store this int. So let's say we get the character let's just get an example. Let's say the letter G. Okay. So the letter G is 7. However, if F gets C doesn't return the G like this. It will actually have an extra whole heap of zeros at the front. Oops. Because it's returning an int. Okay? So we have all these zeros. And what we do is, because it needs to be stored inside a car, is these get cast away. Okay. And so we get left with our character, and our character gets stored in CH. So CH is here now. So we have 0, 1, 0, 0, 0, 1, 1, 1. It then needs to compare with ELF, which is not a car, it's an int.
So this gets converted up again. So all the zeros get added back on. Okay. And these aren't equal. So that's perfectly fine. Okay. Because it's not end of file. Now, we get to the state where f gets c returns end of file. Okay. So it returns 0x f, 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 f. Okay. And then it needs to store it in ch, so it gets rid of all of these top parts. So we have ff, and that gets stored in ch, and so now we've got the comparison 0x ff with an int. Now if this is unsigned, and this is getting even deeper, then this number is just a whole number, and so zeros just get added on to the front. So even though this was EOF, the problem is that we have an infinite loop. Okay. So that's the unsigned case. Now we go to the signed case, which is the dangerous case. So the unsigned case is the infinite case. As I said, car could be either signed or unsigned. So we return ELF from fgets, which is saying that it's at the end of the file. And we get this beautiful end of file. Now it gets stored into a car, so we lose these top part. And car now holds 0xff, and it's signed, okay? It then has to do a comparison with EOF. Now, because it's signed, it needs to be converted up. So it actually adds all these f's back. Okay. So it does the comparison. It works. Or does it? No, it doesn't work. So this is unsafe. Why? Because what if the character return was FF? So let's do that case. So F gets C actually gets the character FF. I think I've got too many zeros. Whatever, close enough. It then gets converted to a car, so we lose these zeros. It then needs to do the comparison with ELF. It's a -1 because it's signed. And so the character FF now thinks that it's end of file. And this case doesn't come up very often, but it is really bad. The general rule is that you should always use an int with these kind of things. And I bought the crap out of everyone I've got left.
Alright, I'm gonna finish up there. Thanks heaps. Didn't still good.